Hi, welcome back. And today we're going to be teaching you about gravitational potential energy. My name is Daniel Kim and I'm joined by... And today we're going to show you a great PowerPoint on this topic.
Gravitational potential energy. Gravitational potential energy is energy an object possesses because of its position in a gravitational field. The most common use of gravitational potential energy is for an object near the Earth, where gravity is 9.8 meters per second squared. However, the gravity can be changed due to its environment. For example, if there are two masses in outer space, then the gravitational force between them is 6.67 times 10 to the negative 11th power, Newton mass squared.
So here are some equations that you should know. On Earth, potential energy or gravitational potential energy equals the weight times height, which is mass times gravity times height, and it's in joules as its units, and gravity is 9.8 meters per second squared. In space, however, gravitational potential energy equals negative gravity times mass of 1 times mass of 2, all divided by the radius. This is also in joules, and gravity is 6.67 times 10 to the negative 11 nanometers squared over kilograms squared. Force, or F, equals negative g times mass of 1 times mass of 2 divided by r squared, and this is in newtons. Gravity is also 6.67 times 10 to the negative 11 nanometers squared divided by kilograms squared.
Problem number 1. A 50-kilogram hang glider is flying up at an angle of 30 degrees next to Mount Rushmore. If she starts at the bottom of the mountain and flies to the top for a total distance of 50 meters, what is the change in gravitational potential energy from the bottom to the top? So in this equation, we know that the mass is 50 kilograms of the person. Gravity is equal to 9.8 meters per second squared. Height 1 at the beginning of the mountain is 0 meters, and at the top it is 50 meters at an angle. But since it is in the y direction, you multiply that by the sine of the angle, which is 30, so that'll be 50 times sine 30. So the change in potential energy would be the energy at the top subtracted from the energy at the bottom, which would be 50 kilograms times 9.8 meters per second squared times 50 sine 30 minus the energy at the bottom, which is 50 kilograms times 9.8 meters per second squared times 0, because the height is 0, which would make the whole entire potential energy at the bottom of the mountain 0. So that would be 12,250 joules minus 0, and that would be the final answer.
Okay, to show you why U equals F, or force, here's a equation to show you why. So U, or W, equals the negative integral of negative force. So when you plug force in, which is G of mass 1 times mass 2 all over r squared, once you integrate that equation, you find that it is negative g m of 1 times m of 2 over r. But since there's a negative on the outside, the two negatives cancel out to give you positive g times mass 1 times mass 2 over r.
Problem number 2. What is the gravitational potential energy of the moon with respect to the Earth? The mass of the moon is 7.35 times 10 to the 22nd kilograms, and the mass of the Earth is 5.98 times 10 to the 24th kilograms. The distance from the Earth to the moon is 384,400 kilometers. So we know the mass of the moon is 7.35 times 10 to the 22nd kilograms. The mass of Earth, which is little m, is 5.98 times 10 to the 24th kilograms. Big G, the force of gravity, is 6.67 times 10 to the negative 11th nanometers squared over kilogram squared. The radius, or the distance between the center of the Earth to the moon, is 384,400 kilometers. And so we plug that all into G times big M times little m over r, and we get negative 6.67 times 10 to the negative 11 nanometers squared over kilogram squared times 7.35 times 10 to the 22nd kilograms times 5.98 times 10 to the 24th kilograms, all over 384,400 kilometers. And the final answer is negative 7.63 times 10 to the 22nd megajoules. Problem number 3. There's a two-particle system where one particle weighs 3.6 kilograms and another particle weighs 5.7 kilograms. The gravitational attraction of the particle is negative 4.5 times 10 to the negative 13th newtons. What is the gravitational potential energy of the two-particle system? If you triple the separation between the particles, how much work is done by the gravitational force between the particles? So, once again, we're going to define our variables. So big G is, again, 6.67 times 10 to the negative 11 nanometers squared over kilograms squared. Big M is 3.6 kilograms, little m is 5.7 kilograms. Thus, the force is negative 4.5 times 10 to the negative 13th newtons. So, in order to find the force of gravitation, it is negative G times big M times little m over r squared. If you use simple algebra, you find out that the radius of the equation is negative G times big M times little m over F, and the whole thing is square rooted. Thus, you plug in your variables, so negative 6.67 times 10 to the negative 11 nanometers squared over kilograms squared times 3.6 kilograms times 5.7 kilograms, all over negative 4.5 times 10 to the negative 13th newtons, and all of that square rooted. The final answer you get is that the radius is 55.1499 meters.
Since you already have the radius, now you need to find what the gravitational potential energy is. So we know that U equals negative G times big M times little m divided by R. So we plug in everything that we know now that we have the radius, and we find that the gravitational potential energy is 2.483 times 10 to the negative 11 joules. Now that we have the gravitational potential energy, we want to find the work done when the separation is tripled. So, in order to find that, we know that when the separation is tripled, the radius is tripled. So to find the change in gravitational potential energy, we do negative G times big M times little m over 3R, since it's tripled, minus the original distance, which is negative G times big M times little m over 1R. And that equals to 2/3 negative G times big M times little m over R. After plugging in everything that we know, now that we know that the gravitational potential energy is 2.483 times 10 to the negative 11 joules, we just multiply that number by 2/3 to find that U equals 1.655 times 10 to the negative 11 joules. And since we know that work equals negative change in gravitational potential energy, we just add a negative sign in front of it to find the work done.
Thanks for watching, and tune in next time for the next video. Physics is fun.
Alright.